adding vectors graphically. We're going to use the tail to tip method. You should have a protractor that looks like this, and a pencil will work best. So my first example, add the following vectors graphically to find the resultant. So a vector has magnitude, which is how big it is, as well as direction. And we can represent each of these with an arrow pointing in the proper direction, and the length of the arrow tells you its magnitude. You have to decide on a scale. For this one, I've decided that 1 centimeter should equal 5 meters per second. I wanted to blow this up a little bit so you could see it. Now, the first thing you do is put in a coordinate system. So the first thing I drew was the black coordinate system. Where I start, I've marked with the letter X. The first vector I drew was 40 meters per second to the south. So if 1 centimeter equals 5 meters per second, I've divided 40 by 5, and my first vector on my graph is 8 centimeters long to represent that 40 meters per second. Its tail begins at the origin and points towards the south. Super important to put that tip in. Your next vector is 60 meters per second to the east. So 60 divided by 5 is 12. I'm putting the tail of the next vector at the tip, the last one I drew, and I draw 12 centimeters and I put its tip on. Notice it's pointing towards the east. My last vector is 10 meters per second to the north. Divide by 5 and you have 20 for your length on your piece of paper. Its tail begins at the tip of the last vector you drew, and I go straight north, and I put the tip in. What you're trying to find is the resultant from your very beginning point, the tail of the first vector you drew, to the tip of the last vector you draw. So I've drawn a line from my origin, where I put my X, to the tip of my last vector, and I've measured that with my ruler, and it's 13 centimeters. I've converted the 13 centimeters back into meters per second, so that's the magnitude of my resultant. The value of the angle you need to measure with your protractor. So I've put my protractor on. With this protractor, the 0 lies right along the line, and I'm measuring up to about 47 degrees. My final answer needs to give the direction as well as the value of the angle. So my resultant is 65 meters per second, 47 degrees north of east. So I started at east and I would go 47 degrees north. Your goal is to take all these different directions. I think of it as a bird flying. The bird might fly south, east, and then north, but he could also fly directly over everything and get to the same destination. Let's try a few more. So in my second example, I have 3 vectors. One's 5 times 10 to the third meters north, 6.5 kilometers south, and then 4 kilometers east. First thing you should notice is that you don't have the same units. So you have to get in the same units to be able to represent it on a piece of paper. So I chose to go to kilometers. I took my 5 times 10 to the third meters, converted it to kilometers, and I see that it's 5 kilometers north. Now I have much easier numbers to work with. My scale is going to be 1 centimeter equals half a kilometer. On your paper, you might find that it's easiest just to say 1 centimeter equals 1 kilometer. I needed a slightly different scale to make it large enough for you to see. First thing to do, draw the X and Y, and I drew it in black first. Then my first vector I drew was 5, which is now 5 kilometers to the north. I began at the origin and drew with my ruler, it has a ruler right along the side, a vector that represents 5 kilometers to the north. So mine is 10 centimeters long because my scale is a little different. My next vector is 6.5 kilometers south. Using my scale, I'll draw it 13 centimeters to the south. So my tail of my second vector, the red, is right on top of the orange because one's going this way, one's coming right back down. It's like you retracing your steps. 6.5 ends just a little bit below the origin. And then I drew my 4 kilometers east. My tail of the vector is at the tip of the last vector I drew, and then to the east. Again, your goal is to find the resultant, which goes from the beginning of where you began the process at your origin to the tip of your last vector. So I just measured that using the ruler part of this protractor. So I got about 8.7 centimeters. Hopefully you'll have a much more accurate number. It's hard with the thick pens. I converted that back into kilometers. Because of my sig figs, I only have 2. I rounded to 4.4 kilometers for my magnitude. The direction, I need to know the angle, and I chose to read this interior angle. I could have read the angle from the x-axis. And if I place my protractor like this, there's the 0 mark, and I read to the black line, my resultant, my angle is 71.0. My final statement is 4.4 kilometers, 71 degrees east of south. South, and then go 71 degrees towards the east, and I should have a tip right here. Let's do another one. All right, this time I've used the unit Newton in my vector. A Newton is just a push or a pull. We'll be working with it in the next chapter. So just consider it a vector unit. It has a direction as well as a magnitude. My first vector is 30 degrees north of west, 10 newtons north, 15 newtons east. So my scale is 1:1, so that makes it nice, I think. My first vector is in blue. I've drawn my origin. I've started with an X, and I've gone 30 degrees north of west. So this angle right there is 30 degrees. So I put my protractor on here and gone 30 degrees. I've drawn it to scale, so I've drawn it about 5 centimeters in length. My next point, I've drawn a little coordinate system so that I can head directly north from the tip of my last vector. I want to draw it 10 centimeters directly north. So I drew 10 centimeters to the north and put a tip on my vector. My last vector is 15 newtons each. So 15 centimeters directly to the east, and there's the tip of my last vector. Draw your resultant from where you began, I've been putting the X there, to the tip of the last vector you drew. When I measure, I have 17.6 centimeters, which converts back to 17.6 newtons. My angle that I chose is the one from the y-axis, and so I placed my protractor like this, and you can read directly this angle right in here, and mine is 40 degrees, and it's east of north. My final statement, my resultant, is 17.6 newtons at 40 degrees east of north. I have one more example for you. This time, let's add these vectors. I have 6 meters per second at 45 degrees south of east, 8 meters per second north, and then 10 meters per second at 20 degrees north of west. So I have 2 that don't lie along the XY. My scale is just 1:1. 1 centimeter will represent 1 meter per second. Put in your coordinate system, Draw an X where you're starting. It doesn't really matter which one you start with. I've just chosen to do them in order, usually because you do that. My first is 45 degrees south of east. So I used my protractor and went 45 degrees south of east. And then I drew it 6 centimeters in length. I put my tip on it. My next vector, the tail of it, goes on the tip of the last vector I drew. My tail is here. I'm going directly north for 8 centimeters. I draw a tip on it. My next one's at an angle, so I need a coordinate system, and I measure 20 degrees north of west. So I used my protractor, measured 20 degrees, it's right in here, and then drew it 10 centimeters in length and put a tip on it. Your resultant, let me label it, put an R right there, is from the tail of the first vector you drew. Again, if you draw an X there, you'll know where to measure your resultant from, to the tip of your very last vector. Put those tips in. Don't skip that little part. Measure your resultant. Mine was 8.3 centimeters. I converted back to meters per second using my scale. To find the angle, this time I found the angle from the x-axis. So to do that, I used my protractor, measured from the x-axis. My angle is 56 degrees, and that is north of west. My final answer, 8.3 meters per second at 56 degrees north of west.